Hey everyone, welcome to today's lesson. In today's lesson, we are on lesson 1-7. In this lesson, what we're going to learn is how to verify that two functions are inverses. Graphically, numerically, and algebraically. Our focus are linear functions. Our language objective is to explain the steps we use when proving two functions are inverses of each other. So let's take a look at our do now. So for today's do now, what we are doing is answering the following. We are asked to find the inverse of each of these two problems. So I'm going to make you guys pause this video, find the inverse of each, and let's see if we have the same inverse functions. So here are my two answers. The first thing we should be looking for when they're asking us to find the inverse is to determine if it is a one-to-one function. So I know I have a linear function, therefore it is a function and it is one-to-one. I end up rewriting the equation in terms of x and y, swapping the x and y's, solving for my new y, and writing my answer in correct inverse notation. For number two, the process is exactly the same. Be careful with your inverse notation here. We had a g function with an a input, so my g inverse of a would be equal to 5a plus 45 over 2. So just be careful with the input that we originally had. So what are we doing today? We are going to prove the inverse of a function. So there is a specific way that you're going to be asked to prove this. There are three different types of proofs that you could do. So steps. You can determine whether two functions are inverses by looking at each of the coordinates of the first function, xy, and the coordinates of the second function would be swapped, yx. Then, if this occurs, that means that we have inverse functions. And this is known as a numerical proof. So just by looking at the ordered pair. 2. In order for two lines to be inverses, they will need to be a reflection over a specific line, and that line is y equals x. And in this case, we have a graphic proof. So by looking at the graph, and if I see that they are a reflection over that line, y equals x, we have two lines that are inverses of each other. The last one, and my favorite, is the composition of functions will be equal to x. And this is our algebraic proof. So you're going to see three different proofs, but the one that we like most would be the algebraic one. So let's look at example number 1. So for example number 1, we have proved whether the following functions are inverse functions, and we're dealing with a graphical proof and also a numeric proof. Given the function f of x and g of x, verify whether the functions are inverses numerically. So for this case, what I'm going to do is I'm going to input these functions into my calculator. I'm going to input into my calculator and look at the table to determine its ordered pairs and just compare based on that. So here's my first piece. If I put the first piece in my calculator and I copy the table, here are some of the values I saw. I'm going to do that again, and I'm going to input my second function. Now, when I am doing this, what I am going to be focused are looking at the y values of f of x. And I'm only going to copy those y values from my new function. The reason I am doing that is because I want to see and determine whether x and y swap. So if this was my original x comma y ordered pair, when I look at g of x function, did my value swap? And I can see in each of these cases that yes, it did. So I can conclude that these two functions are inverse functions of each other. So here's my first piece, my x, y change. Therefore, that's my numerical proof. My graphical proof. So showing this graphically. First thing I'm going to graph on my grid is the line y equals x. So I start off with that y equals x. That's my line of reflection. Now what I'm going to do is graph f of x function and also g of x, and I'm going to use those ordered pairs that I already have from part A. Alright, so I graphed both my functions, g of x and f of x. Make sure you label your lines as well. Again, we have been labeling since algebra, so the process itself of graphing is still the same. What I am going to do is just highlight that line of reflection. And I already know that these two functions are inverse functions of each other. Why? Because of the ordered pair itself. But if I look at each of these specific points, so let's say I pick this point here to focus on, I see that this point is equal distance from the line of reflection. And that occurs in every single place I move. So since they're equally distant from the line of reflection, we have inverse functions. And this would be our graphic or graphical proof. And same kind of stuff, what you would say here is f of x and g of x are inverse functions because they have been reflected over the line y equals x. All right, so here are the two types of proofs you can see. Let's look at the algebraic proof because that one is a little more involved. So here in example number 2, we are proving whether the functions are inverse functions, but this time we're doing it algebraically. So for number 1, given the following functions, we have f of a and we have g of a. Prove and state whether the functions are inverses, and we want to do it algebraically. So how are we going to do this? The first thing we're going to do is we are going to show the composition. So I'm going to show two different compositions. If it holds true, then that means that they're inverse functions of each other. So I'm going to start off with my first function composed of my second function. That's the first thing. And I'm going to try to prove the input. So that's our goal. We're going to do the composition and hopefully I end up at just an A, or the input itself. I also have to do the composition of the second composed by the first. And again, I want to show or prove that A. So I need to show two different cases here. So let's start with the first one. If I have f composed of g of a, I'm going to start off, I'm doing the composition with g of a. And g of a is a plus 3 over 2. If I'm doing the composition, I take that piece and I input it into the second function. So our second function is twice the input minus 3. Remember, our goal is to try to show that we get an A, the input itself. At this point, let me try to simplify, and I see that I can knock out those 2's. I'm left with A plus 3 minus 3. I can also see now I could cross out those 3's, and I'm left with A, which is great because the first piece checks out. I was able to show A. I'm going to do it again with the second piece. So I'm going to start off here with my f of a function. And then I'm going to input that into my g of that new input and see if I am able to show A. All right, so there's my substitution piece. Again, now I'm going to try to simplify. First thing I notice, I could get rid of RB3s. So I'm left with 2a over 2. I can get rid of the 2's, divide by 2, and I'm able to show that A. Super good. Since I'm able to prove both of these compositions, I can conclude that f of a and g of a are inverse functions. For number 2, we have been given two functions, f of x and g of x. Prove and state whether the functions are inverses, again, algebraically. So what we're going to start off with is we want to show the composition piece. So we want to start with f composed of g of x. And our goal is to get x, is to get the input. That's our goal. That's what we want to prove. And we also want to show the composition of g composed of f of x. Also, can we get to x? Okay, so there's my setup. Now that I have that, I'm just going to start substituting and doing the composition flow. So for the first piece, I start with g of x. That g of x goes into f of x. I am going to try to clean this up if possible, right? So I distributed, which helped me out because I'm able to cancel out those 2's, leaving me with an x. So part 1 done. Part 2, let's see if I'm able to prove that x. Start with the f of x function. Input that f of x into g of x. There's my substitution. Again, I am going to clean this up by doing my distribution and seeing if I could cancel out anything, which awesome I can. Leading me to my goal of x. This officially tells me that these two functions are inverse functions of each other. Make sure you write that statement because you have to answer the question, right? We were actually wanting to know and stating whether these are inverse functions of each other. All right, so for number 3, what I would like you guys to do is try this one on your own and let's see if we are able to get the hang of this and get the same answer as me. So here's my work. I wanted to show the composition of f composed of g of n is equal to n. The first piece, I see it did not work out. I was able to show negative n, which is not what we wanted to show. In the second composition, I started off with g composed of f of n. I did the flow of the composition and it led me to negative n plus 18. Again, not our goal, which leads me to conclude that these two functions are not inverse functions of each other. So sometimes we are able to show that they're inverses and sometimes we are not able to. You could double check on the calculator and look at its table to really prove to yourself that you did the algebraic approach correct. So keep learning, keep growing, and I will see you all in my next video.